Hello everyone, I am Nanditha, Assistant Professor from Civil Department, Marri Laxman Reddy Institute of Technology and Management. Today our topic is criteria for design of structures in structural stability subject. So these are the course objective: to derive the differential equations for beams, columns. Next, to understand the elastic buckling of bars and frames, to understand the torsional buckling, to analyze the lateral buckling of beam and plates. Then these are the course outcomes. After completion of the course, students be able to apply the approximate methods based on energy to determine the stability of simple systems, differentiate how the tangent modulus and double modulus theories of inelastic buckling led to the column paradox, thereby preventing further difficulties for a general theory of structures, analyze elastic and inelastic buckling of bars and frames, analyze the beams for lateral torsion buckling. And this is the syllabus from the unit 1, criteria for design of structures. And these are the topics: stability, strength and stiffness, classical concept of stability of discrete and continuous systems, linear and non-linear behavior. And from the unit 2, stability of columns, axial and flexural buckling, lateral bracing of columns, combined axial, flexural and torsional buckling. Unit 3, stability of frames, member buckling versus global buckling, slenderness ratio of frame members. And Unit 4, stability of beams, lateral torsional buckling, stability of plates, axial flexural buckling, shear flexural buckling, buckling under combined loads. And from the Unit 5, introduction to the inelastic buckling and dynamic stability. Now, introduction. So, what is structural design? The process of determining the safe and economical shape, size, and material of structural members ensures that structure can resist loads, remain stable, and limit deformations. Or, this is also the definition: structural design is the art and science of creating a structure that can safely withstand loads and environmental effects throughout its service life. Key steps in structural design: define design requirements, load, environment and material, check stability, strength and stiffness, verify serviceability and economy. The purpose: to ensure the structure performs its intent function safely, efficiently and economically. To maintain stability, strength and stiffness under all expected conditions. Structural safety: protection against failure or collapse under extreme loads, based on load and resistance factors, IS codes. Serviceability: structure must remain functional and comfortable during usage. Example: control of deflection, cracking and vibration. Durability: should resist weathering, corrosion and aging. Economy: achieving optimum cost without compromising safety or performance. Summary: structure design is including all these factors: safe, serviceable, durable and economical. Basic principles of structural stability: equilibrium condition, geometry and support conditions, adequate stiffness, load path continuity, material strength, avoidance of buckling. Equilibrium conditions: for a structure to be stable, the sum of all forces and moments must be 0. Geometry and support conditions: the geometry of members and the type of supports, fixed, hinged, roller, play a key role in stability. Example: a simply supported is more stable than a cantilever of the same span. Adequate stiffness: members must have a sufficient rigidity to resist lateral or buckling deformations. Stability decreases as slenderness increases. Load path continuity: load should be transformed smoothly from one to another until reaching the foundation. Discontinuous cause instability or collapse. Material strength: the material should be sustained stress within the allowable limits. Proper factor of safety must be considered. Avoidance of buckling: columns, compression members and thin plates must be designed to prevent lateral instability. Next, Euler's buckling concept is key. Father of structural stability is Leonhard Euler, a Swiss mathematician, physicist and engineer. Introduced the concept of buckling of columns, formulated the Euler's critical load. The formula is as follows here: pi square EI by KL whole square. E modulus of elasticity, I moment of inertia, L effective length, K column effective length factor. Contributions: developed the theory of elastic buckling, a foundation of stability analysis. His work laid the groundwork for modern structural and stability analysis used in civil and mechanical engineering. Concepts introduced by Euler are still applied in columns, trusses, frames and shells. Fundamental design criteria: every structure must satisfy strength, stability, stiffness. Stability, equilibrium under load; strength, capacity to resist stress; stiffness, resistance to deformation. Each criterion affects safety and usability. Stability, ability of a structure to maintain equilibrium after being disturbed. A stable structure returns to its original position after disturbance. Example, column under axial compression. Types of equilibrium: stable, neutral, unstable. Stable returns to equilibrium. Example, suspended pendulum. Neutral stays in new position, rolling cylinder. Unstable moves away from equilibrium, buckling column. Stability failure, buckling. Buckling, sudden sideways deflection due to compression. The critical load, pi square EI by KL whole square, depends on material length and end conditions. Example, long slender column failure. Strength, the capacity to resist loads without material failure related to stress, strain and material properties. Type, tensile strength, compressive strength and shear strength. Factors affecting strength: material quality, concrete, steel and timber. Type of loading, static, elastic and static, dynamic and impact. Type of loading, static, dynamic, impact. Cross section dimensions, environmental effects, corrosion, temperature, stiffness. Resistance of a structure to elastic deformation, expressed as K is equal to F by rho. Important for serviceability, prevents cracks and vibrations. Example, beam deflection control. Significance of stiffness: ensure comfort and aesthetic performance, prevents excessive deflections and cracks, maintains alignment of structural alignments. Relationship between stability, strength and stiffness. Property: stability, strength, stiffness. Stability, equilibrium condition, prevents collapse. Strength, load resistant and ensures safety. Stiffness, deformation control and ensures serviceability. Discrete systems, system with finite degree of freedom. Example, 2D frames, pin jointed trusses, multi-story buildings. Stability analyzed using stiffness matrix methods. Continuous systems, infinite degrees of freedom, distributed parameters. Examples, beams, plates and shells. Governed by differential equations of equilibrium. Comparison: discrete versus continuous systems. Discrete, degree of freedom is finite. Example, truss and frame. Analysis type, matrix method. Continuous, degrees of freedom is infinite. Example, beam and plate. Analysis type is differential equation. Linear structural behavior: load, deformation, that is Hooke's law. Load directly proportional to deformation. Valid within the elastic limit. Sigma is equal to E modulus. Example, small deflection in RCC beam. Easy to analyze mathematically. Non-linear structural member. Load not proportional to deformation. Occurs beyond elastic limit or due to the large deformation. Types: material non-linearity, yielding and cracking. Geometric non-linearity, large deflection. Boundary non-linearity, support changes. Linear versus non-linear comparison. Load deformation: in linear it is proportional, in non-linear it is non-proportional. Deformation: In linear it is small, in non-linear it is large. Analysis: in linear it is simple, in non-linear it is complex. Example: small beam deflection in linear, plastic hinge formation in non-linear. Thank you.